the practice exam, problem 12. Find the magnetic distance B, a distance D above a square loop of wire. Using that result, show that the magnetic field inside a big solenoid is equal to the result that we know for a solenoid. However, this turns out to be a lot more complicated. You have to evaluate integrals. I didn't want you to have to evaluate any integrals. Really what I meant to do is show that it's independent of L, and that we can do without evaluating any integrals at all. All we have to do is do a little analysis of what the integrals are. So that's what I'm going to do. I'm going to find an integral expression for the magnetic field at this point for the loop, and then I'm going to write down what the magnetic field for an infinite solenoid would be, and show that in the limit as this solenoid is infinite, it's independent of L. So looking at that, let's go ahead and write this down. We are going to use Biot-Savart law. The Biot-Savart law says that the magnetic field for a loop is given by the following formula. You have mu naught times the current flowing through the loop divided by 4 pi. And then you have an integral around the loop dl cross script r all over the magnitude of script r cubed. So now we have to write down what script r is. For us, we kind of know the r is always your source point. That's where your, not source point, is your field point. That's where you want to evaluate. So for us, r is here. It is just going to be dk hat. Script r, okay, is your, or script r prime is your distance to your source point. So for us, the source is some little differential current element here. So this is script r. So this is not script r, that's r prime. And r prime is going to be in the x direction. So if we make a typical x, y, z coordinate section. In the x direction, it's L over 2 I hat plus y j hat. And here, right, I'm defining this distance there as y. Now, script r is, of course, the vector between these two, and so script r is just r minus r prime, right? It's r prime, which is minus L over 2 I hat minus y j hat plus d k hat. And so that's the script r vector for this guy. So now we just need to plug them in. Oh, we need one other thing. This is our little differential element, this dl vector. It's going to point in the y hat direction, right? The current here is flowing in the y hat direction. It's actually flowing in the negative y hat direction. So this is minus minus dy j hat. And so if I do the minus dy, I have to evaluate from a positive to a negative. So I evaluate along the direction. So I have to start at the positive, end at the negative. That's going to get rid of that minus sign there. So let's just start plugging stuff in here. The last trick I'm going to use is I'll just look at one loop of this, and I know that by symmetry my magnetic field will only be in the z direction, so I'll only look at one loop and take the z component. So the magnetic field that we're going to be looking at is going to be 4, because I'm going to take the one leg here, mu naught I over 4 pi. Then here's this trick. I have to go from plus L over 2 to minus L over 2, because this is my starting point and that's my ending point. And then I'm going to get dy, and now I have this j hat cross minus dy, so that's the minus there. I have j hat cross the r hat, and I only care about the z direction, right? So let me just go ahead and write this down. J hat cross the script r, and I'm only going to care about the z component of that, so I'm going to get the k hat vector out of that. And this is over the script r cubed. For here, we can evaluate this. J hat cross I hat gives us the k hat that we want. J cross I gives us a positive or j cross I gives us negative k hat to cancel with a negative, so we're going to get an L over 2 out of that. So the magnetic field in the end for dk, right, is going to be, the 4's will cancel, I'm going to get an L over 2, so this will be mu naught I L over 2 pi. Then I have an integral. I'm going to swap the limits of this integral, so go from negative L over 2 to positive L over 2, get rid of that minus sign. Minus L over 2 to positive L over 2 dy. I'm left over, I have the k hat from there, I just bring that out front. And that I've already written, that was the L over 2, so now I just have to write this. So this is 1 over quantity L over 2 squared plus d squared plus y squared to the 3 halves power. So this is the first part of the problem, which is find the magnetic field a distance d above a square loop of current. Don't have to worry about actually evaluating the integral. We have an expression that, if you evaluate, would give you the magnetic field. So we want to keep working with this and figure out what the magnetic field inside this loop would be, or this solenoid. So if we made lots and lots of these, what would the magnetic field inside that be? So what I'm going to do is, let's look at some point here in the center, and let's say at a distance z up from that point in the center, we look at a band here of width dz. And what I'm going to say is that the magnetic field for the solenoid is going to be equal to integral from negative infinity to infinity, so over all space, of dz, and then some differential element here, this b, db is a function of z, which is what I have. So this is this b of z, although I have to be careful about what I plug in for the I. What I want for the I is the amount of current in this width dz. Oh, sorry, there's no dz here. What I want for the I here is the amount of current in the width dz. And so the I from here, this I, is going to be equal to ni dz. And so that's it. So now I'm going to just plug that in. And so the magnetic field for the solenoid, made out of this stuff, is, I'm just going to copy this down. I get mu naught n I L over 2 pi k hat, then an integral from negative infinity to infinity dz, the integral from negative L over 2 to L over 2 dy, 1 over the square root of quantity L over 2 squared plus z squared plus y squared to the 3 halves power. So this is the expression that ideally I would like to evaluate, and that I ask you to evaluate. But here I'm going to make it a little bit simpler on us. I'm not going to find out exactly what it is. What I'm going to do is simply show that this whole expression should be independent of L. And to do that, all I'm going to do is I'm going to factor L out of this guy and do a change in variables on z and y. And I'm going to pull those out. So going ahead, the first term, let me just rewrite this, 1 over L over 2 quantity squared plus z squared plus y squared to the 3 halves power is of course equal to, I can factor this L over 2 out. This is going to equal to 8 over L cubed, that's factoring the L over 2 out, and 1 over 1 plus 2z over L quantity squared plus 2y over L quantity squared to the 3 halves. And now I'm going to do two changes of variables. I'm going to let 2z over L go to z bar, then dz goes to L over 2 times dz bar, And my limits from negative infinity to infinity don't change, of course. Now the other one, of course, is dy, or 2y over L is going to go to some y bar. And now my integral from minus L over 2 to L over 2 dy is going to be equal to L over 2. This is that change in variables from the dy to the y bar, minus 1 to 1. So my limits will no longer reference L dy bar. Now I can rewrite this magnetic field for the solenoid is equal to mu naught n I. I'm going to actually borrow the 2 here, so this will be over pi times k bar. I'm going to borrow this L over 2, and notice what I'm going to do. I have an L over 2 from the dz integral, I have an L over 2 from the dy integral, I have an L over 2 from here. So I get L cubed over 8 times this one, 8 over L cubed. Yay! Cancels out. Now negative infinity to infinity, dz bar, negative 1 to 1, dy, 1 over 1 plus y squared, y bar squared plus z bar squared to the 3 halves. And so we get the result that at least we show that it's independent of L. So we kind of knew this before. It doesn't matter how big your solenoid is or what shape it's in. And so here we've shown that it's independent of the size of the solenoid. We've shown it for a circular thing. Also, because we know the answer, we've kind of proven a second thing, which is we now know that 1 over pi should be this integral here. So there's another kind of thing that we've shown. So that's it. That's all we need for this type of problem. So it'll be the same on the exam. I don't want you to evaluate any of these integrals. I might want you to show some property, but I won't need you to explicitly evaluate any of these integrals.